Good morning, sir.
Good morning, everyone.
Good morning, sir.
Good morning, sir.
Good morning. Let me just project everything. So slides are visible to everyone?
Yes, sir.
Yes, sir.
Okay. So just a quick recap of what we have discussed in the last class. So the most important thing is we are going to follow a book, Heat Transfer by BK Datta. So if you have not purchased it, you purchase it from Amazon or whatever the source you wanted to purchase. Again, it is available online if you wanted to get it. I don't know how to get it, but you can get it online also. Okay. So core strategy, this was one of the point which has, pointed by some students. So credit is 4. Yes, you are absolutely correct. So 310. So credit is 4. Okay. So other than that, those who have not attended the last class, I will just take 1 minute and then we will go to the summary of the last class. So we will have minor 1 30 marks. We will have 2 quizzes. So out of 2 quizzes, we will have best one will be counted. Again, each quiz will be 30 marks each. Since we are counting a best out of 2, there will not be any re-quiz if you miss. And if you miss both the quizzes, then you lose all 30 marks. Major will be 40 marks, so that total becomes 100. Okay. Again, all the quizzes and examinations will be conducted on Moodle and questions will be numerical type. Again, the classes and the tutorials will be conducted on MS Teams. Grading will be relative and audit pass grade is 30 marks and above. Okay. So all yes, please go ahead.
Sir, the numerical part is just for the quizzes or for the minor and major as well?
Everything will be numerical and connected questions.
Okay, sir. Paragraph based, something like 2-3 questions for each paragraph. That's all.
2-3 questions connected. So depending on what answer you have given in the last part, you can solve the next part. Something
okay,
like
sir,
that.
got it. Yes.
So even if you have made some mistake in the previous part but done the next part correctly, you will get the full marks. Something like that. Okay. So we started in the last class the description on the heat transfer and why heat transfer is important. So again, to give you a recap, if you look at the process applications, heat transfer is one of. Yes, please go ahead.
Sir, can you please explain like the symbols used in this diagram, like this Z symbol and that
So that
downward
Z
and upward
symbol
arrow?
is that is kind of, that symbol is used for the heat exchanger. If you look at the standard symbols, these are used for heat exchangers. Okay.
Okay, sir.
So these are just the heat exchangers. I have not used exactly the convention, but this Z symbol or something, these are used for the heat exchanger. Okay. Okay. So we have seen that in the last class that most of the process applications, they require commonly the heat transfer. For a simple process like nitric acid production, you can clearly see there is a refrigeration, there is a heating, and then there is a heat recovery also, isn't it? So the generality and ubiquity of the heat transfer in the process industry makes the heat transfer one of the most important subject for the chemical engineering and biochemical engineering. Okay. Again, I will not go in a detail of this. This we have already seen in the last class. So there are 3 modes of heat transfer: conduction, convection, and radiation. One of the most commonly used modes are the conduction and convection. Again, if you look at the conduction is a molecular process. So heat transfer takes place by the drift of the electron or the vibration of the lattices. Again, in conduction, you will not see any macroscopic movement of the material or a particles. So conduction is the mode of heat transfer without any macroscopic movement of the particles or molecules, fluid particles. Okay. Again, the conduction is governed by a Fourier's law of heat conduction that we have already seen in the last class. Next mode is the convection. So convection, in convection, basically you will see that there will be a macroscopic movement of the fluid particles are there. So the movement of the particles or the displacement of the fluid elements are generally caused either by the external pressure gradient due to some pumps or agitators, etc. So this type of convection is called as a forced convection. Also, the movement of the fluid elements may be caused by the density difference. If the liquid at the bottom is at a higher temperature and the liquid at the top is at the lower temperature, then the liquid particles at the bottom try to move upward because of the density difference, and this type of convection is called as natural convection or a free convection. Again, the heat transfer is governed by Newton's law of cooling, so that we will see later on. So Newton's law of cooling roughly is heat flux is proportional to the temperature difference. Okay, the third important mode is the radiation.
Sir, how does temperature difference create a density gradient?
So see, if the temperature is higher, then the density decreases, isn't it? Density of the liquid decreases as the temperature increases, isn't it? So that becomes lighter at the bottom. Density is also a function of temperature, isn't it? So because of that, these particles at the bottom becomes lighter compared to the particles at the top, and therefore these try to move upward. And this causes the displacement of the fluid elements.
Okay, sir. Yes, sir. Thank you.
Okay. The last mode is the radiation. Radiation again do not require a medium. The radiation heat transfer can be given as is proportional to the fourth power of the absolute temperature. That is what is the Stefan-Boltzmann law. Again, it depends on two important things. One is the emissivity and another thing is a view factor. Emissivity is again compared with respect to a standard, and the standard is referred as a black body. Black body has the emissivity equals to 1. Again, view factor is nothing but it takes into account the fraction of the area of the body which can be seen by the other body. Okay. So here you can see the body at a lower temperature also radiate. It's not that the body only at the higher temperature radiates, and the net heat transfer is calculated. So that is nothing but how much is the difference between the heat, the radiation heat absorbed by a particular body and the radiation amount of radiation is emitted by the body. That difference will give you the net heat transfer. Okay. So with this quick recap, then we have started looking at the steady state conduction in one dimension. Steady state conduction in one dimension. Again, the steady state word is very important. If you look at when we are saying the steady state, that means it does not depend on the time. Again, the sufficient time is given in order to have the equilibrium. That is what it means. Okay. So a simple example of a plane wall we have taken, and in this particular plane wall, you can see on the left hand side the temperature T1 is there, and on the right hand side the temperature is T2. T1 is higher than T2, and therefore heat will be transferred from T1 to T2. Again, this heat transfer through a slab will be governed by a Fourier's law of heat conduction, and the Fourier's law of heat conduction is given as the heat transfer, the net heat transfer Q is given as Ka T1 minus T2 divided by L. So here T1 minus T2 is nothing but the driving force, whereas L by Ka is nothing but the resistance offered by the slab. Again, the slab has the thickness of L and the cross-sectional area is A. Okay. So here you can see in the Fourier's law of heat conduction what we are saying, that the net rate of heat transfer Q will be proportional to the the temperature difference and inversely proportional to the thickness. Correct. And the proportionality constant here is going to be K. So where K is nothing but the thermal conductivity. Okay. Now the Fourier's law of heat conduction in a differential form is given in this way, where Qx is nothing but the heat flux which is proportional to the temperature gradient dt by dt, and the proportionality constant is K, where K is nothing but the thermal conductivity, which is the property of the material. Like viscosity, like diffusivity, K is also a property of a material, and the unit of K is watt per meter degree Celsius or watt per meter per Kelvin. Okay. Again, here you can see the negative sign is because the heat is transferred from higher to lower temperature. So this anyway we have seen. I am just quickly giving you the recap of what we have done in the last class. So the important property here is the thermal conductivity. Thermal conductivity is a property of material which gives a measure of the effectivity of the material in transmitting heat through it. Okay, it depends on chemical composition. It depends on whether the material is solid, liquid or gaseous. It depends on whether the material is crystalline, amorphous. It also depends on the physical conditions like temperature and pressure. Generally, in crystalline material, the heat is transferred by the vibration of the crystal lattice, and therefore the crystalline material will have a more thermal conductivity compared to the amorphous material. Also, the thermal conductivity is also depends on temperature. So for solids, the thermal conductivity of the metals generally decreases with the increase in the temperature, and also it decreases with the increase in the impurity. So unlike this, if you look at the insulators, the thermal conductivity increases. That was the question in the last class, isn't it? So for insulators, thermal conductivity increases with the temperature, because if you look at the most of the insulators, they generally have a foam-like structure. So most of these foam-like structures has the void volume is present, in which the gas is present, inert gas is present, and the thermal conductivity of the gases increases with the temperature, and therefore the thermal conductivity of the insulating material increases with temperature. Okay. Also here one thing to note down is the insulating property of the thermal insulators is primarily because of the gas entrapped in this void. Okay. For liquids, thermal conductivity decreases with temperature, whereas for the gases, thermal conductivity increases with the temperature and it decreases with the increase in molecular weight. Okay, so this is what we have seen in the last class. Again, the thermal conductivity, if you look at a typical range, thermal conductivity of the solids will be higher than the liquid, and liquid will be higher than the gases. Order of magnitude, around 2 order of magnitude difference is there. For example, if you take silver, for silver the thermal conductivity is 410. That is a typical order of magnitude if you look at the thermal conductivity of the solids. For water, the thermal conductivity is 0.63 watt per meter Kelvin, and for air it is 0.0262 watt per meter Kelvin. Again, thermal conductivity is a weak function of temperature. Most of the cases thermal conductivity is taken as a independent of temperature and average value is taken. But in general, the thermal conductivity is a function of temperature, and the relationship can be given here. K is given as K0 1 plus AT plus BT square. So this type of relations are also used whenever there is an appreciable change in the thermal conductivity when the temperature changes from one point to another. Okay. So this is what we have seen. Again, if we apply a Fourier's law of heat conduction to a composite solid wall. So here you can see there are 3 composite walls are there, and if we apply a Fourier's law of heat conduction, what we get is the temperature difference. So if we apply a Fourier's law of heat conduction for the first layer, we can get the net rate of heat transfer Q is given as K1A T1 minus T dash divided by L1, where T1 is the temperature outside this first slab and T dash is the temperature at this interface. Again here K1 is nothing but the thermal conductivity of the material 1, and similarly we can write down the expression for the layer 2, layer 3. If we add all these expressions, what we get is the net rate of heat transfer Q, which is going to be same in all three slabs because it is a steady state case. Again the area is common for all three walls, and therefore Q1 is equals to Q2 and Q2 is equals to Q3, and these all are equals to just Q. So we can obtain Q as T1 minus T2 divided by the total resistance. Now total resistance here is what? The resistance in the first layer, resistance plus resistance in the second layer, and the resistance in the third layer. So resistance in the first layer is going to be L1 divided by K1A. From this equation itself, you can find out the resistance one. Here you can see the resistance is L1 divided by K1A, and the driving force is going to be T1 minus T dash. So this is the resistance. L1 divided by K1A is nothing but the resistance for the slab 1. Similarly, the resistance for slab 2 is going to be L2 divided by K2A, and for third slab it is going to be L3 divided by K3A, and all three resistances are additive, and therefore this is given in terms of a current flow diagram as you can see here. So the left hand side there is a T1, on the right hand side there is a T2, and there are three resistances in series. So R1 is nothing but L1 divided by K1A. Similarly, R2 is nothing but L2 divided by K2A, and R3 is L3 divided by K3, and all three resistances are additive. Okay. So total resistance in this case is going to be R1 plus R2 plus R3. So this is just a simple application of Fourier's law of heat conduction to each of these slabs, and based on this the temperature difference is obtained for each slab, and these temperature differences are added in order to get the overall temperature difference T1 minus T2, and if we rearrange this equation, finally we get this equation. Q is given as total temperature difference divided by total resistance. So total temperature difference is going to be T1 minus T2 divided by total resistance RT is nothing but R1 plus R2 plus R3. Okay. So this is what we have seen in the last class. This is a very simple case. Again, I will not go in this detail. This we have already discussed. This example we have solved in the last class. There are several other examples are also there in the book. Please go through all the examples. I am not going to take all the examples in the class. So there are many examples solved in the book. I will only look at some selected examples. Okay. Okay. So this is what the recap of the last class. So sorry, I have rushed through the previous material because that anyway we have covered in the last class. Okay. Now let us look at the steady state heat conduction through a variable area. This is a very important topic. So far we have seen a composite wall or a wall in which the heat transfer area A was fixed, isn't it? A was not changing. You can go back and see here this heat transfer area A is fixed for all three slabs, isn't it? So rate of this heat transfer area is constant for all three slabs, and therefore if you look at the temperature profiles are linear here. You can see the temperature profile in slab 1 is linear, slab 2 is linear, and slab 3 is also linear because we are looking at the steady state heat conduction, and also the heat transfer area is constant, is same for all three slabs, and there is no heat generation, there is no accumulation. And therefore the temperature difference, the temperature profile is linear here. Of course, the slope of these temperature profiles are different in each of these slabs depending on what is the value of thermal conductivity used for each of these slabs. Okay. Now, unlike this, we can have a cylindrical surface area like this, where outside temperature here is T0. And the inside temperature here is, let's say, Ti. So the heat will be transferred from inside to outside or outside to inside through this radial surface area depending on what is the value of Ti and T0. Okay. So now here you can see the heat transfer area heat transfer area varies depending on what radial position we are looking at. For example, if you are looking at this radial position shown by this shell here, which I have made, which is at the radius r. So here you can see radius r is higher than Ri, but it is smaller than radius r0. So clearly the heat transfer area, which is nothing but this radial surface area, is going to be higher for this cell compared to this Ri, this inside surface area, whereas it is going to be lower than the surface area offered by the cylinder at the outside. Okay. So heat transfer area is going to vary as we move along the radial direction. So this is a hollow sphere where the heat transfer takes place from the radial surface area. Okay. So similar examples we can have for a spherical geometry, where also as we move from the center to outside, depending on what radius we are looking at, the heat transfer area is going to vary. Okay. So unlike a previous case of a plane wall where heat transfer area was constant, but here the heat transfer area is varying as we are moving along the radial direction. Okay. So now let's look at the steady state heat conduction for all such cases where heat transfer area is varying as we are moving along the radial direction. So let's take the example of a cylinder. Again, here we are looking at the temperature inside this hollow cylinder is Ti. The temperature outside of this hollow cylinder is T0. There is a heat transfer taking place between the outside and inside. Again, the outer radius is R0, inside radius is Ri, and in order to solve this particular problem, since the heat transfer area is varying, we have to make a shell balance here. So let us consider a element or a cylindrical element or a shell at a radius of r. So this shell is shown here, which is shown by a dashed lines here. So this cylindrical shell is assumed at the radius of r. Okay, so heat flow occurs in a radial direction. Area of heat flow varies from 2 pi RIL inside to 2 pi R0 L outside. So here you can see the outside surface area is 2 pi R0 L, whereas the surface area inside is 2 pi RIL. Okay. Again, the thickness of the cell is delta R. So let's make the heat balance for this particular case. So rate of heat input to the shell at the radial position R. So we are making a heat balance at this shell which is at the radius of R. So let's make the heat balance at this shell which is at the radius R. So rate of heat input to this shell at the radial position R will be given as the area of heat transfer into flux. So that can be given as the area of heat transfer is going to be 2 pi RL and the flux is QR, and this entire thing has to be calculated at the position R. Similarly, the rate of heat output from the shell at a radial position R plus delta. Remember the thickness of the shell or the element, cylindrical element which we have used for the balance, the thickness of that is delta R. So outside area of the shell is going to be what? R plus, what is the outside radius of the shell is going to be R plus delta R, isn't it? So the rate of heat output from the shell at the radial position R plus delta R is going to be again the area into flux, and area in this case is going to be 2 pi RL QR, and this entire quantity has to be calculated at R plus delta R. Correct. Again, in this particular case, there is no accumulation. There is no accumulation and there is no generation term. There is no generation term. So clearly, whatever is the heat input to the shell, that should be same as the heat going out from the shell, isn't it? So heat output from the shell should be same as heat input to the shell. So that we can equate here. So this output is equated to the input here. And if you rearrange the terms and divide by delta R, what we get is a expression in a differential form. So here we can get 2 pi RL QR at R plus delta R minus 2 pi RL QR at R divided by delta R, and that should be equal to 0. So clearly the delta R, which is nothing but the thickness of the shell, which should be approaching to 0, isn't it? Because that is the elements of delta R we have selected, isn't it? So this particular expression can be represented in a differential form as d by dr 2 pi r L QR equals to 0. Okay, again 2 pi L, these are the constant values, isn't it? So L is a constant value. Here you can see L is not varying, so L we can take out from this differential. 2 pi is again constant and 2 is also constant, so we can get 2 pi L out from this equation. So finally what we get is d by dr r QR equals to 0. So this is the equation obtained from the shell balance. Now if we integrate this particular equation with respect to R, what we get is RQR equals to constant, and let's say this constant is C1. So RQR equals to C1. This equation is equation number 1. Now here QR is nothing but the heat flux. Remember the heat flux QR we can obtain from the Fourier's law of heat conduction. So QR can be given as minus K dt by dr, where K is the thermal conductivity of the cylindrical material, whatever we are looking at, and dt by dx is the temperature gradient. So we can put QR equals to minus K dt by dr in this equation number 1, and we can simplify. Okay. So if we put this Fourier's law of heat conduction in this equation, what we get is equation number 3. So which is nothing but R in the bracket minus K dt by dr equals to C1. If we rearrange this equation, what we get is dt by dr is equals to minus C1 by K into 1 by R. Again, if we integrate this entire equation with respect to R, what we get is T is given as minus C1 by K ln R plus C2. So this is the expression which we have obtained, equation number 3. Now here C1 and C2 are the integrating constants, and these we have to obtain by using the boundary conditions. So now what are the boundary conditions? If you look at this particular shell, what are the boundary conditions? The boundary conditions are here when R equals to Ri, when the radius R is equals to the inside radius Ri. In that case, the temperature T is equals to Ti. Similarly, when radius R is R0, in that case, the temperature is T0. These are the boundary conditions. So that is what we have looked at here. So this is the expression which we have obtained, equation number 3. We have applied the boundary conditions here. So R equals to Ri, the temperature T is Ti, and when R equals to R0, temperature T is T0. If we put these boundary conditions in this the final equation number 3, what we get is Ti is equals to minus C1K ln Ri plus C2, and T0 equals to minus C1 by K ln R0 plus C2. Again, we can subtract both these equations. So by subtracting both these equations, the C2 will get cancelled out, and we can get common as a C1. So C1 can be obtained as minus T1 minus T0 K divided by ln R0 by Ri into ln R by Ri. So this is the value of constant C1 we are going to get by mathematical substitution of these two equations. Similarly, if we put C1 in this original equation in this equation, if we put C1, we can find out C2. So C2 can be obtained as Ti plus Ti minus T0 ln Ri divided by ln R0 by Ri. So once we get C1 and C2, we can put it in this equation number 3, and putting this, what we get, the temperature distribution, and the temperature distribution is obtained as T is equals to Ti minus T0 divided by ln R0 by Ri into ln R by Ri. So equation number 4 is the temperature distribution. Now here one thing to note down, unlike a flat slab in which we have obtained, I can go back to the flat slab again. Unlike this flat slab, here you can see the temperature distribution is linear. Temperature distribution is linear here. Here you can see the temperature distribution is linear. So this temperature distribution across each slab is going to be linear. Unlike this, if we look at this temperature distribution is not linear. This is not linear. Why? Because the area is not constant. Area, heat transfer area is varying as we are moving from Ri to R0. As we are moving along a radial direction, my heat transfer area is varying, and therefore the temperature distribution is not going to be linear as we have seen for a flat slab. Okay. Okay. Now, based on this temperature difference, we can now find out the rate of heat flow. So rate of heat flow Q can be obtained as okay. So rate of heat flow Q, remember, even though the temperature distribution is not linear, but still we are looking at the steady state, condition, steady state condition. That means whatever is the heat flow, that is going to be constant, isn't it? That is going to be constant along the radial direction. So at any R, this Q is going to be fixed. This Q is going to be fixed. So area is varying. So heat flux is going to vary, isn't it? But this multiplication of these two at any R is going to be constant because we are looking at the steady state condition, isn't it? So whatever heat input is there, that should be the same as the output, and therefore this Q should be same. Okay. So based on this, the area is 2 pi r L. 2 pi r L is the surface area into QR is nothing but the heat flux at any R, and this multiplication should be constant. So we can go back and look at this equation. So remember, QR we can directly obtain here. RQR we are directly obtain as C1, isn't it? RQR is nothing but C1. So we can use equation number 1. In this equation. So the Q can be obtained as 2 pi L C1. Remember, 2 pi R L QR is there. So RQR is nothing but C1. That is what we have seen from equation number 1. RQR is nothing but C1, which is constant. So we can put RCR is as C1, and remaining is 2 pi L. So 2 pi L C1 is nothing but the total heat flow, rate of heat flow Q is given as 2 pi L C1. So rate of heat flow 2 pi is given as 2 pi L C1. So C1 we have already obtained here from the boundary conditions. So C1 is obtained as this. So we can put the C1 here. We can put the C1 here. So by putting it, what we are going to get is two pi L K Ti minus T naught divided by ln R naught by Ri. So that is what we are going to get it. Okay.
So how about the balance terms?
Which balance you are saying?
So that negative sign and that ln thing in the numerator.
Okay. So see here, let's say we start from equation number 3. Equation number 3 which we have obtained here, isn't it? This is okay. Equation number 3 is correct.
Yes, sir. Yes, sir.
Okay. Now in equation number 3, let's apply the boundary condition. So apply the boundary condition. So at R equals to Ri, T is Ti, isn't it? So this becomes Ti equals to minus C1 ln Ri, isn't it? Plus C2. Correct. Similarly, T naught equals to minus C1 by K ln R naught plus C2. Correct?
Yes, sir.
Is it correct? Now let's subtract these two equations. By subtracting, what you are going to get, this C2 will get cancelled out, isn't it? This C2 will get cancelled out, and what you are going to get is Ti minus T naught, and Ti minus T naught is going to be what? This C1 you can get common C1 by K, isn't it? And you are going to get ln R naught minus ln Ri. This negative sign will not be there. I'm sorry. This negative sign.
And sir, also that part in the numerator, I guess. ln R by Ri.
Which one?
So on the right side in the numerator,
This
this one.
Okay, just wait. This negative sign will not be there, and what you are saying, the
Sir,
R by
C is a
Ri will not
constant.
be there. Let me just
Can
look
be
at it.
function of R.
It'll be constant, na, so how can we have it dependent on R?
Yes, just wait. Let me just check where I have. Okay, yes. This part, this is just a cut paste thing. Sorry, this will not be there. Yes. Thank you. So this C2 is correct. Hello.
So didn't solve for C2 right now.
C2 is correct, right?
Yes, sir, probably.
Okay. So then you can put C1 here, so that becomes ln R.
Yes, sir, it is correct. Yes, sir, it is correct.
Now it is everything is correct.
Yes, sir.
Okay. Thank you. So this expression, this last expression is also correct. Okay. Okay, let me just maximize it. Okay. So rate of heat flow is obtained here. Q is obtained as 2 pi Lk Ti minus T naught divided by ln R naught by Ri. Now here one thing to note down is what is the driving force here? The driving force is nothing but Ti minus T naught. Ti minus T naught is the driving force, whereas ln R naught by Ri divided by 2 pi Lk is nothing but the resistance. So Q, rate of heat flow, is given as the driving force divided by resistance. So that is what is shown here. Okay. So this is nothing but the driving force, whereas the thermal resistance is ln R naught by Ri divided by 2 pi Lk. So again, if we rearrange these terms, so remember we are getting in the denominator ln R naught by Ri, isn't it? But we wanted to express this equation similar to the expression which we have obtained. Remember this equation we wanted to represent similar to the expression which we have obtained for a flat slab. So for a flat slab, what was the denominator? Denominator which we have obtained was a thickness of the slab, isn't it? L. If I go back and just show you a flat slab, what is the denominator here? L1, isn't it? L1 or L. So thickness is there. So let us present this equation in a similar manner. So again here, in order to have the thickness at the bottom, thickness will be what? R naught minus Ri, isn't it? So that is going to be the thickness of the cylindrical slab, isn't it? So we can rearrange this equation slightly in order to have R naught by Ri, and we can multiply this in the numerator R naught by Ri. If we do that, then this entire equation can be represented in a slightly different manner. So R naught minus Ri divided by ln R naught by Ri, this is nothing but the logarithmic mean radius, of the cylinder. So if we represent this R naught minus Ri divided by ln R naught by Ri as a Rm, where Rm is nothing but the log mean radius, then 2 pi Rml, this will be the area. But this area is calculated based on the log mean radius of the cylinder. So area into K into delta T divided by thickness of the cylindrical slab. So this equation will be similar to the expression which we have seen for the flat slab. Okay, clear? The only difference here is going to be the area calculated in this case is going to be the area based on the log mean radius of the cylinder. Log mean radius of the cylinder. Is it clear to everyone? So if you wanted to analyze this particular expression with respect to the expression which we have obtained for the flat slab, the only difference we are going to have is the area will require in this case will be a area based on the log mean radius. Log mean radius. Okay. Okay. Now similar to this, let's move to another case of the sphere. Okay. Sorry. So this is extended. This idea of the flat slab is then extended. The expression of the rate of heat transfer is extended for the composite cylindrical wall. So here we are having 3 composite cylindrical wall. And again here, if we obtained the expression for Q, the expression for the Q can be obtained as here again Ti is the temperature inside, T naught is the temperature outside, T dash and T double dash are nothing but the temperature at the interfaces, interface of the cylindrical slab 1 and 2, and T double dash is between 2 and 3. Again, K1 is the thermal conductivity of the material 1. K2 is the thermal conductivity of the material 2, and K3 is the thermal conductivity of material 3. So here the rate of heat transfer Q is obtained as 2 pi Lk1 Ti minus T dash. So Ti minus T dash, this T dash is at this interface here. So Ti minus T dash is going to be the temperature difference for the first cylindrical slab here divided by ln R dash by Ri, because R dash is going to be the outlet here, the radius at this interface. So R dash by Ri. So that will be 2 pi Lk, and that will be equals to the heat transfer at the slab 2, and that will be equals to the heat transfer at the slab 3. Remember here we are looking at the steady state. So that means Q1 should be equals to Q2 should be equals to Q3. Okay. So again, for the second slab, we can write down the expression as 2 pi Lk2 T dash minus T double dash divided by ln R double dash by R dash. Similarly, that should be equals to 2 pi Lk3 Ti minus, sorry. So this should be T double dash minus T naught. Okay. This should be T double dash by T naught. Okay. Okay, so now it is correct. Okay. So we will have here again for the third slab, it is going to be the temperature gradient is going to be temperature difference is going to be T double dash minus T naught and divided by ln R naught by R double dash. Okay. So if we add the temperature difference, if we can calculate the temperature difference for each of the slab and add these, what we are going to get is Ti minus T naught. And if we rearrange this entire thing, what we are going to get is Q is given as Ti minus T naught. That is nothing but the overall temperature difference divided by the individual resistances. So the resistance for the first slab is going to be ln R dash by Ri divided by 2 pi Lk1 plus ln R double dash by R dash divided by 2 pi Lk2. And similarly for the third slab plus ln R naught by R double dash divided by 2 pi Lk3. So here this is the resistance for the layer 1. This is the resistance for layer 2, and this last is nothing but the resistance for layer 3. Okay. So is it clear to everyone? So this is just the extension of the Fourier law of heat conduction for the composite wall, composite cylindrical wall. So here we are having 3 cylindrical walls concentric to each other. Can we move to the next slide? Is it clear?
Yes, sir.
Okay. Okay. Now let's look at the case of sphere. Similar to cylindrical case, the sphere case also, as we move along the radial direction, as we move from center to the radial direction, as the radius increases, my heat transfer area, my radial heat transfer area is going to vary, isn't it? So clearly, again, in this case also we need to make a shell balance. We need to make a shell balance. Remember, we have not made any shell balance for the case of a flat slab because there the heat transfer area was constant. Okay. Again, two more things. One more thing which we have to remember is in a flat slab, the temperature profile is linear, isn't it? The temperature profile is linear and the heat transfer rate Q is same for all the flat slabs, all the slabs present in the composite slab, isn't it? So unlike that, whenever there is a variable area for uh, uh, the case of, let's say, cylinder and the sphere, one has to make the shell balance because the area is varying, the heat transfer area is varying. That is one thing. The another thing is the temperature profile is not going to be linear. That is the second thing. And the third thing is the heat transfer rate of heat transfer Q is going to be same for all the concentric slabs you are having in a cylindrical geometry as well as in a spherical geometry. So these are the 3 things one has to remember. Okay, let's make the shell balance.
So can we say that small QR is varying in case of
small QR, yes,
non-slab
small
things
QR is varying. Yes, small QR is
and capital
varying.
Q is constant?
Capital Q is constant. Yes,
For
sphere
slab,
as
small
well as
QR is
cylinder.
also constant.
Again, please come again.
So for slab, small QR is also constant.
Yes.
Okay, sir.
That is why we don't need to make a shell balance in case of a flat slab. We need to make a shell balance for a flat slab whenever there is a accumulation or a generation term is there. There is no generation term, there is no accumulation term. And therefore, we have not made any shell balance for a flat slab. If you go back and see, we have not made any shell balance there. Okay, clear?
So here what is being generated or accumulated?
There is no accumulation and there is no generation so far. We will take those cases later.
Okay, sir.
We will look at those cases. Right now, there is no accumulation, there is no generation. Clear?
Sir, what if we take 3 different materials, slab type materials of different areas and combine them together?
In a flat slab, you are saying?
Yes, sir. Not of same area, but different areas.
If you are having the area difference, in that case also it is not varying gradually. Remember, when we make a shell balance, when it is varying gradually, then we make a shell balance, isn't it? Correct. In that case, when you are saying that in a flat slab, I can go back. Yes, you are. It's a very good question in a way. See, for example, you are saying for slab 2, I make, let's say, a slightly bigger area, isn't it? Correct.
Yes, sir. Yes.
So in that case, maybe I can increase the height of the area, height of the slab 2. That is what you are trying to say.
Yes, sir. Yes, sir.
In that case, this area A which we have kept constant A, that will vary. But still you are going to get a linear profile because you are not going to make a shell balance here because that is that is not a gradual increase, isn't it? That is not a gradual increase along the length. Whenever you are having a gradual increase along the length, then definitely you need to make a shell balance. In fact, one of such question is an unsolved problem in the book. One of such question is an unsolved problem in the book. In fact, one of such problem we will also solve in the tutorial, if I am not wrong. Okay.
So today we'll be having a tutorial.
Yes,
or
we
is it
will
not?
have a tutorial 2 to 3, isn't it?
Yes, sir, it is. So it'll be held on Teams for group 1.
Yes, group 1 and 3.
Yes, sir. Yes, sir.
Yes, it will be held on the team, same team.
Okay, sir.
Okay.
Thank you.
Okay. So again, go back to the sphere case. Okay. Okay. So what will be the rate of heat input to the shell? Again, we have assumed a shell of thickness delta R at a position R. Okay. So what will be the heat input to this shell? The heat input to this shell is going to be the area, which is nothing but 4 pi r square, isn't it? Now we are looking at the sphere, isn't it? This is a sphere. So for spherical case, the area is going to be 4 pi r square into the heat flux QR, and that has to be calculated at the position R. Similarly, the rate of heat output from the shell, just a minute, somebody messaged me. Okay. So is it visible? The slides are visible?
Yes, they are, sir.
Okay, sorry. So now what will be the heat output from the shell? The heat output from the shell will be given as 4 pi r square QR, and that has to be calculated at the position R plus delta R, isn't it? What will be the position here? R plus delta R outside the shell. Correct. Again, at steady state, we are assuming that the rate of heat accumulation is 0. There is no generation term, and therefore rate of heat input should be same as rate of heat output. Correct. So these two terms are going to be same. So we have equated here these two terms. So what we are getting here is 4 pi r square QR at R plus delta R should be same as 4 pi r square QR at R. So if we rearrange this equation in a differential form, what we get is 4 pi r square QR at R plus delta R minus 4 pi r square QR at R divided by delta R should be equals to 0, where delta R is tends to 0. Clear? So this equation can be represented in a differential equation form. So what we get is d by dr. What we get is d by dr is d by dr in the bracket 4 pi r square QR equals to 0. Again, 4 pi is a constant term, so we can get rid of this term 4 pi. So what we get ultimately from this is d by dr is equals to r square QR equals to 0. If we integrate this equation with respect to R, what we get is R square QR should be equals to constant. Let's say this constant is C1. Okay. So this is the equation number 1. So this equation we have obtained from the energy balance across the shell. Now from the Fourier's law of heat conduction, the flux QR can be obtained as minus K dt by dr. So we can put QR equals to minus K dt by dr in equation number 1. So what we get is R square minus K dt by dr equals to C1. If we rearrange this equation, what we get is dt by dr is equals to minus C1 by K into 1 by R square. And if we integrate with respect to R, what we get is T is given as C1 by KR plus C2. So we get equation number 2 after integrating this equation, we get equation number 2. So this is nothing but the temperature profile along the radius R, and here C1 and C2 are the constant. So let's calculate the constant C1 and C2 using the boundary conditions. So this is the equation number 2. Again, we wanted to find out C1 and C2 using the boundary conditions. So boundary conditions are when R equals to Ri, T is Ti, and when R equals to R0, T is T0. So these are the boundary conditions which we are having. We can apply these boundary conditions to this equation number 2 and simplify the equation number 2. So what we get is, by simplifying equation number 2, what we get is Ti is obtained as C1 divided by KRI plus C2, and similarly T0 is obtained as C1 divided by KR0 plus C2. And if we subtract this second equation from equation number 1, what we are going to get is C1. So C1 is obtained as K Ti minus T0 Ri R0 divided by R0 minus Ri. Just check whether this is correct. And similarly, if we put C1 in this equation, we can obtain C2, and C2 is obtained as Ti minus Ti minus T naught R naught divided by R naught minus Ri. Just check whether these C1 and C2 are correct. Is it correct?
Yes, sir.
Okay, thank you. So then we can put this C1 and C2 in equation number 2 and we can obtain the temperature distributions. So temperature distribution obtained here is Ti minus T naught R naught divided by R naught minus Ri in the bracket 1 minus Ri by R. Check whether this is correct. Temperature distribution equation. Is it correct? Just we have to put C1 and C2 in equation number 2 and check whether we are getting the same expression as this temperature distribution equation. Is it correct? Anyone?
Yes, sir. Seems to be so. Yes, sir.
Okay. So again, unlike the flat slab, here you can see the temperature distribution. If you look at, it's not linear. It's not linear. You will not get a linear profile. You will get a parabolic type of profile. You will have some curved lines. You will not have a straight lines. Okay. Clear? So again, the rate of heat flow you can obtain directly from the previous equations. Okay. So remember the rate of heat flow in this particular slab is going to be constant. So Q is going to be same as QRI, QR naught, isn't it? So so Q is going to be constant, isn't it? And that can be given as the area into flux at any radial position R, isn't it? Area into the flux at any radial position R. That is what we have written here, isn't it? Area into heat flux at any R. So what is area for pi R square QR, isn't it? Is equal to constant, and that is given as Q. Now R square QR that we have anyway obtained earlier, isn't it? This is the R square QR. R square QR is nothing but constant C1, isn't it? From equation number 1. So we can put R square QR as a C1 in this equation. So we can replace R square QR from this equation as C1, which we have already obtained here, this C1. So if we put it, what we get is the rate of heat flow Q is obtained as 4 pi C1. So 4 pi C1, if we rearrange all the terms, what we get is 4 pi Ri R naught K Ti minus T naught divided by R naught minus Ri. Now, again, this particular equation, we can compare with the equation which we have obtained for the flat slab. So here you can see Ri into R naught, which is there in the numerator, Ri into R naught. This can be represented as a geometric radius, isn't it? So if we take this as a square of the geometric radius, in that case 4 pi Ri R naught is nothing but the area calculated based on the geometric mean of the radius, isn't it? So this will be area. 4 pi Ri R naught is going to be area into K Ti minus T naught divided by R naught minus Ri. So this is going to be the same expression as that of what we have obtained for a flat slab. The only difference here is going to be the area calculated is based on the geometric radius, geometric mean area. The area is going to be the based on the geometric mean radius R. Okay. Again, for the composite sphere, we can write down the final expression for the composite. Suppose there are 3 concentric spheres are there, spherical, slabs are there. In that case, the Q can be obtained as total temperature difference, that is Ti minus T naught divided by the individual resistances. So individual resistances are going to be R dash minus Ri divided by 4 pi Ri R dash K1 plus R double dash minus R dash divided by 4 pi R dash R double dash K2 plus R naught minus R double dash divided by 4 pi R double dash R naught K3. Here K1, K2, K3 are going to be the thermal conductivity of material 1, material 2, material 3. If we are looking at the composite sphere of 3 layers. 3 layers, layer 1, layer 2, layer 3. Okay, clear? So is it clear?
Yes, sir.
Okay. So this is similar to the composite cylinder we have seen. So that is why I have directly given this expression without more detail. Okay. Okay, now let us add some more complications. So we remember how we have started. We have started with a very simple case of a flat slab where no shell balance was required because the area was constant. Steady state we have assumed there was no accumulation, there was no generation term. Okay. Then we have moved to a slightly complicated case of cylinder and sphere where again we have assumed the steady state, no accumulation, no generation, but the heat transfer area was variable. Heat transfer area was varying as we were moving along the radial direction. So heat transfer area was a variable. Now let us move to a slightly more complicated case where in addition to the usual things which we have seen so far, let us assume that there is a heat generation is present. Let us assume that there is a heat generation is present. There is no accumulation, but there is a heat generation. Now, such cases are very important because such cases are commonly seen in the process industry. For example, if you look at the nuclear reactor. So nuclear fuel, that is kind of a cylindrical structure, and there is a continuous bombardment of the neutron is taking place on the nuclear fuel element, and because of that the heat is generated inside the cylinder. So there is a generation term is present. Another case could be, we can take the example of the electrical wire. Electrical wire, generally a metal wire is there. Outside of this metal wire there is a insulator is there. But if you look at this metal wire, the current is flowing through this metal wire, and since even though the metal is a good conductor of the electricity, but this will also have some resistance, and because of this resistance the heat will be generated inside the metal wire, and this heat will be dissipated on a radial direction, and therefore the insulator which is outside of this electric wire, that will not only act as a insulator for the electric current, it also act as an insulator for the heat also, isn't it? Okay, clear? The third example could be a catalyst pellet. A spherical catalyst pellet is there, and there is a heat generation taking place inside the catalyst pellet because of the chemical reaction taking place inside. Okay, so these are the common examples. These are the common examples seen in a process industry where there is a heat generation is also taking place. Okay, there is a heat generation taking place. Now, whenever there is a heat generation taking place in all such cases, you can see there will be a, in general, the thermal conductivity is taken as a function of temperature. Thermal conductivity is taken as a function of temperature. Remember, so far in all the balances, we started from the flat slab, we have moved to the cylindrical structures, then we have moved to spherical structures. We have assumed thermal conductivity constant, isn't it? But this thermal conductivity can also be a function of temperature. In all such cases, one need to make a shell balance. Remember, whenever there is a area varying, whenever there is a thermal conductivity varying, whenever there is a accumulation term, whenever there is a generation term, all these, whenever any of these is present, you need to make a shell balance. This is the bottom line. This remember. Okay, clear? So let us consider our simple case of a flat slab. Remember, in a flat slab case, we have not used any shell balance, but now you will see we will make a shell balance here because there is a generation term is there. There is a continuous heat generation is taking place inside. Okay, so consider a plain wall of a thickness L. So there is a thickness L, small l. I'm sorry. Let me just correct it. This is a small l. and the cross-sectional area is still constant, same as A, but there is an internal heat generation is taking place. There is an internal heat generation is taking place. The temperature at one end is T1 and the temperature at another end is T2. So T2 here and T1 here. The heat is transferred from T1 to T2 and we are looking at the temperature distribution along the X direction. So X is starting from here. So X is 0 here. And as we are moving along this, there is a X direction this. So this, if we consider a element here of delta X thickness, which is at the location.
Hello, sir.
Yes, please go ahead.
So we
So we
can't
are
see the
not able to see the
presentation.
slide.
Okay. Let me just. So how much time?
It is last minute only.
So 14
Okay.
minutes.
Okay. Let me share the slide again. Okay. Okay. Can you see the slides now?
Yes, sir.
Please interrupt
Coming up.
me in between. Whenever these slides are not visible, please interrupt me in between because whenever I am, explaining, I am only on the slide. I am not able to see the window of this MS Team. Okay, so I don't get to know whether slides are visible or not. So please interrupt me whenever such things happens. Okay. So now slides are visible.
Yes, sir.
Okay. So let us take the example of again a flat slab. The only difference here is now in this particular flat slab, uh, there is a heat generation is taking place. So this flat slab is of the length L, small l. It transfer area, cross-sectional area here is A. Again, there is an internal heat generation and the temperature at one end is T1, temperature at another end is T2. And we are looking at the heat conduction from T1 to T2. Okay, so we are looking at the heat conduction along the direction X. Let's consider a element of thickness delta X at the distance X from this left hand side. Okay. Okay. So as I said, whenever there is a generation term is there, whenever there is a accumulation term is there, whenever there is a temperature dependent thermal conductivity is there, whenever there is a variable area is there, in all such cases we have to make a shell balance. Now here area is constant. But there is a heat generation term is there. There is no accumulation, but there is a heat generation is there. And therefore, we still need to make a shell balance here. Okay, so let's have a shell balance here. So rate of heat input to the element at position X will be again area into the flux Qx at the location X. Similarly, the rate of heat output from the element at position X plus delta X is going to be AQX at the position X plus delta X. Correct. And the rate of heat generation in the element is given as A delta X, that is nothing but the volume, into psi X. Psi X is nothing but the volumetric rate of heat generation. So volumetric rate of heat generation multiplied by volume, that is going to give me the rate of heat generation in the element. Is it clear to everyone? Now here we are assuming that psi is a function of X. Psi is a function of X. That is what we are assuming right now. But we will simplify this case later. Okay. Again, at steady state, there is no accumulation term. So accumulation term is 0. So what we can write here, the balance is going to be rate of heat input to the element plus heat generation, and that should be equals to rate of heat output from the element. Okay, so that means what? AQX at X plus the generation term, which is nothing but A delta X psi X, and that should be equals to AQX at X plus delta X. So we can rearrange the terms. By rearranging the terms, what we are going to get is minus QX at R plus delta R. Sorry. This is going to be X plus delta X. Okay. So qx at x plus delta x minus qx at x divided by delta x plus psi x equals to 0. This is going to be the expression we will get from uh, the uh, the energy balance. Again, in a differential form for delta x tends to 0, we can write down this equation as minus dqx by dx plus psi x equals to 0. Is it clear? So that is equation number 1. Is it clear to everyone?
Yes, sir.
Okay. So now again qx, which is nothing but a heat flux. Heat flux again we can obtain from the Fourier law of heat conduction. So that can be obtained as minus kt dt by dx. So here we are assuming that k is also a function of temperature. K is also a function of temperature. Okay, so if you put everything in this equation, a generalized equation, what we are going to get here is d by dx minus kt dt by dx plus psi x equals to 0. Okay. Now here this kt is also a function of temperature and psi x is a function of x. Okay. So this particular equation number 2 is a generalized expression. So let's make some assumption in order to solve this equation number 2. So let us assume that k is independent of temperature. So k is fixed as kt is fixed as just a k. Whereas psi x, which is also a function of x, let's assume that psi is uniform everywhere and psi x is given as psi v, which is nothing but the volumetric rate of heat generation, which is constant throughout this solid, which is not varying along the length x. So with these two assumptions, we can solve this particular equation with the boundary conditions. Now the boundary conditions in this case are x, when x equals to 0, t is t1, and when x equals to L, t is t2. Remember, in this case, when x equals to 0, t is t1, and when x equals to L, t is t2. So these are the boundary conditions. And again, the simplifications we are assuming here are the kt remains constant as k. So thermal conductivity is not varying with respect to temperature, and we are assuming it to be a constant value k. Similarly, psi x is not varying along the x direction and it is uniform throughout the solid and is equals to psi v. So with these two assumptions, this equation number 2 can be simplified as delta square t, d square t by dx square is given as minus psi v by k. Okay. So this expression again we can integrate twice with respect to x, and by integrating with respect to x twice, what we are going to get is t is given as minus psi v by 2k x square plus c1x plus c2, and this is equation number 3. So equation number 3 we will get for these assumptions and by integrating equation number 2. Now in this equation number 3 there are two constants c1 and c2. Constant C1 and C2 we can obtain by applying the boundary conditions. So if we apply the first boundary conditions, so at x equals to 0, t equals to t1. So what we are going to get here is t1 equals to this entire term is going to become 0 because x is 0. This second term is also going to become 0. So C2 is equals to just t1. So the constant C2 is going to be just t1. If we put that constant in this equation and also apply a second boundary condition. So second boundary condition is T2 is given as minus psi v divided by 2k L square plus
Sir.
C1L.
Sir, we are not able to see slide 25.
Slide 25. I'm in 24. Sorry, 25. Okay. Let me just share again. Slides are not visible or slide 24 is visible.
So when you were in 24, we were able to see 24. Now we are on 25, we are able to see 25.
Okay.
It's live.
So there is some lag is there. Okay. So can you see the slide again?
Yes, sir, this is visible.
Okay. Okay. So this is the expression number 2, which is the generalized expression where we are assuming that the thermal conductivity is also a function of temperature, and also the volumetric rate of heat generation psi is also a function of x. but we are assuming that for simplicity, we are assuming kT to be constant, and that is equals to K. So thermal conductivity is not a function of temperature, and we are assuming a constant value K. And similarly, we are assuming that the psi x, which is a function of x, is constant and is constant throughout the solid and is equals to psi v. Okay, so with these two assumptions, we can apply the boundary conditions. The boundary conditions are when x equals to 0, T is Ti, and similarly when x equals to L, T is T2. So if we apply these two boundary conditions to equation number 2, what we, if we apply these assumptions to equation number 2, we can simplify that. So equation number 2 can be simplified as d square T by dx square equals to psi v by k. Remember, when kt is not a function of temperature, we can take it out from this equation number 2, and therefore we can have a simplification here. Okay, so from equation number 2, we can obtain d square T by dx square equals to minus psi v by k. We can integrate it twice. By integrating twice, what we get is T is given as minus psi v by 2k x square plus c1x plus c2, and now we can apply boundary conditions, these boundary conditions given here. So from the first boundary condition at x equals to 0, T is T1. So what we get is T1 equals to just C2. When we apply a second boundary condition at x equals to L, T2, T is T2. So T2 is given as minus psi v by 2k L square plus C1L plus C2, and C2 can be replaced by T1. So if we rearrange this, what we get is C1 is obtained as T2 minus T1 by L plus psi v by 2k L. So just check whether this expression of C2 expression of C1 is correct or not. Just check the expression of C1 is correct or not. Is it correct? So psi v is it correct?
Yes, sir.
So now if we put C1 and C2 in this
So where
equation,
would L square go? L would be getting divided or something of that sort?
here you can see L is divided to T1, T2 minus T1. Remember, that is why this L square gone from here.
Okay, sir. Okay, sir.
Okay. So if we put C1 and C2 in this equation number 3, the temperature distribution we are getting, which is nothing but T1 plus T2 minus T1 x by L plus psi v x by 2k L minus x. So clearly here you can see the temperature distribution is not linear. Okay. Now let us calculate the heat flux Qx. So remember, this was the expression which we have obtained, minus dqx by dx plus psi v. So from equation number 2, if we go back, equation number 1, so dqx by dx is equals to minus psi x, isn't it? So that psi x will become psi v. So minus dqx by dx plus psi v equals to 0. That is equation number 1, isn't it? From this equation, if we integrate, what we get is qx is given as minus psi v x plus c naught. This c naught is a different constant. Okay, but this c naught will be same as minus kc1. Remember, here we have separated in terms of temperature and then we have integrated, isn't it? Here this equation we have integrated, by taking kt out and separating it, isn't it? So C1, this C1 is related to this constant, integrating constant C naught, as C naught is given as minus Kc1. Can you just check?
So your pointer is lagging, so we're not able to understand this last part. That how are
Okay.
you relating the C naught wala part?
Okay, so this expression is correct. This expression, can you see? Minus
So
dqx
which one? Your
by dx.
pointer is not pointing at anything, sir. Matlab
At the bottom, just look at the bottom. At the bottom, minus dqx by dx plus psi v equals to 0. Is it correct?
Yes, sir.
Okay. Now we can integrate this equation.
Yes, sir, we did.
So after integration, what we are going to get is Qx is equals to psi v x plus C naught. C naught is another constant.
Yes, sir.
Why I am saying C naught is another constant and not C1? Because here we have not separated Qx in terms of t. Remember, Qx is k dt by dx, isn't it? So here k we have taken out on the right hand side in equation number 3. Can you see d square t by dx square equals to minus
Yes,
psi
sir,
v
we've
x?
not involved the dependence of Q on X. We have considered them independent right now.
Correct. So here, if you relate this C naught with C1, C naught is nothing but minus KC1. If you relate equation number 3 and equation, this another equation dqx qx equals to psi v x plus C naught. If you relate these two equations, you will see that C naught is nothing but minus KC1. Not able to see this? Are you able to?
Partially able to see it because KT was multiplied up there.
Yes,
But
yes. But minus sign will also be there because here this minus sign is there. D square t by dx square, there is a minus sign. Remember, d square t by dx square equals to minus psi v by k.
yes, sir.
And here you can see qx. If you look at it, qx dqx by dx will be what? Just psi v.
Yes, sir. Yes, I got it, sir. There'll be
So
minus sign.
minus sign, therefore C naught is going to be minus kc1.
Yes, sir.
Correct. So if you put here C1 we have already obtained. So if you put C1 in this equation, what we are going to get is qx is given as psi v x minus k T2 minus T1L plus psi v divided by 2KL. This is the final expression. Again, this expression, this minus sign is, this particular expression is given incorrect in the book. Just check. Okay. This expression is given incorrectly in the book. Okay. Is it correct?
Yes, sir. Yes, sir.
Okay. So we stop here. We will look at the cylindrical wall with a heat generation in the next class. Cylindrical and spherical wall with the heat generation in the next class. Clear? We stop here unless you have any doubt, any question, if you wanted to ask me.
Sir,
Is
does
there
QX always increases or it may decrease as well?
what you are saying?
Does QX always increases with X or it may decrease as well in some cases?
No. See, let me just go back to this. Okay. So now here we are assuming that there is a heat transfer taking place from T1 to T2. Correct? Are you able to get it?
Yes, sir. Yes, sir.
Okay. So that means what? If we are not taking any generation term, what we are going to get? A linear profile. Linear profile means there is a straight line from T1 to T2. Correct?
Yes, sir.
Now we are having a heat generation term. So see, when we are having a no heat generation term, in that case qx is going to be minus k dt by dx, isn't it?
Yes, sir.
Okay. Now if there is a heat generation term, what will happen? How the temperature profile will look like? So from T1, temperature profile is, see, when there is no generation term from T1 to T2, it is continuously decreasing, isn't it?
Yes, sir.
I can go back to the slab and then explain you. Just wait. For example, from T1 to T2, let's say this is T2, this is going to be continuously decreasing as shown by a red line here. Clear?
Yes, sir.
Can you see the red line here in the first slab?
Yes, sir.
So from T1 to, let's say, T dash, it is continuously decreasing. But when there is a generation term, this will not be a continuously decreasing. It could be a curve like this, which could have a higher value than the previous value. So that means what? That means what? When there is a generation term, then this Q, you cannot say that it is continuously decreasing. It can be increasing also depending on what is the generation term.
So
Are you
if there
getting
is
my
no
point?
generation, if there is no heat source or generation, then it will always be decreasing.
Yes, then it is always be decreasing. That is why in a Fourier's law of heat conduction, that will be minus k dt by dx, isn't it? But if there is a generation term, additional factor is added, isn't it? Which will also lead to a Q, isn't it? Correct, isn't it? So Q will be not only contributed by this Fourier's law, but also this additional generation term is also going to contribute in that, isn't it? Heat flux. Correct? Are you getting or not?
Yes, sir. I got that.
So it will not be always negative. It can be positive also whenever there is a generation term. That is what coming here, isn't it? Remember here it can be positive also in the last expression. Can you see?
Yes, sir.
Sir, you mean QX becomes negative entirely that way?
I am saying depending on how the generation term is, in between at any x, remember, and at any x it could be higher than the previous value. It could be higher than the previous value also depending on what is the value of psi v.
Okay, sir.
Psi v and k.
In general, QX is decreasing only, but
In
it
general,
at some
QX is decreasing, but whenever there is a generation term, it could be increasing also. That is what I'm trying to say. And that is what this final expression is also showing. Correct?
Yes, sir. And sir, for the tube, do we have certain sheets to actually solve before, or maybe?
I will put it in the teams today. The question and the solution we will discuss in the tutorial class. Clear?
Okay, sir. Okay, sir. Thank you, sir.
So we
Yes,
stop
sir.
here. Yes, please go ahead.
Sir, QX can also increase now if area is gradually decreasing.
QS can
Also increase if area is gradually decreasing because Q.
Yes. You are right. You are absolutely right. Yes. Because QX into area that should be constant. Yes, you are right. Is there any more question?
So could you please repeat again?
So whatever your friend had said that QX can be increasing if the area is gradually decreasing. Remember area into QX that is constant.
Right, sir. Right. Got it.
So if the area is decreasing, QX will be gradually increasing.
Yes,
Correct?
sir. Yes, sir. Thank you, sir. Sir, if possible, could you please attach these slides? So these are really insightful. If you could actually refer
Let me
these along.
think. I'm not saying no. Let me think. Probably I will upload it also. But let me think because all the material I have taken it from the book. Why I am not uploading? Because otherwise you guys will not go through the book. My take on this is if I don't upload it, then you will definitely go through the books. And in the I am not covering the entire material from the book. Some material is there, some soiled examples are there in the book, which I want you guys to go through. Because it is not possible for me to discuss each and every solved example from the book. Definitely I will do some of the unsolved examples also. Okay. But at least the solved examples you should able to go through.
Yes, sir. We try our best. Sir, also we don't have a digital version for the book. It's just a scanned copy. So if you have a digital copy, could you please share
No,
with us?
I do not have the scanned copy because see, you can see all these equations I have written myself. I have not copied it from anywhere, isn't it?
Yes, sir.
So even the figures I have not copied from the book. I have made all the figures again. So these are I have the hard copy with me because that is not costly. It's just 300 rupees, if I am not wrong. 300 or 350. So
Yes, sir.
that
We
is
search
just
on
kind
it.
of purchasing one pizza.
Yes, sir. Definitely.
Okay.
Thank you,
So
sir.
I think many of your friends might be having.
Sir, I wanted to ask, what about the design projects? Sir, in previous lecture in CLL 121, Professor Gaurav sir discuss about the design projects. So are there any design projects for this
No,
course as well?
we will not have any design projects in this particular course. We will have a plain course, as I have clearly mentioned in the course strategy. Otherwise, I would have mentioned.
Okay, sir.
So where's the tute sheet uploaded?
I will upload it on the Teams. Teams, you can see there are the material section is there. Let me just show. Wait. Files is there, isn't it? In these files, I will upload. In the files, if you go inside, there will be class material or something. There I will upload it. Okay. I have not uploaded so far, but I will upload. Okay. Is it clear?
Yes, sir. Thank you, sir.
Okay, so see you then batch 1 and batch 3 around 2 o'clock. Isn't it?
Yes, sir.
Okay, so I'm unsharing everything. Okay.